Welcome to today's problem walkthrough. In this session, we'll tackle problem number 1538, titled Guess the Majority in a Hidden Array. We'll explore the challenge, discuss approaches, and break down the solution step by step. Let's dive in and uncover the key insights to solve this problem effectively. Here, the problem is called Guess the Majority in a Hidden Array. You are given a hidden array of size n, which consists only of 0s and 1s. However, you don't have direct access to this array. Instead, you can interact with it using a special function called guess. This function allows you to query the array by providing three distinct indices, I, j, and k, which must all be within the bounds of the array. The function will return 1 if the majority value among the three elements at hidden I, hidden j, and hidden k is 1, and it will return 0 if the majority value is 0. Your goal is to find the index of the majority element in the array, which is the value that appears more than n/2 times. If there are multiple indices for this majority value, returning any one of them is acceptable. However, if no majority element exists, the function must return -1. The input consists of the hidden array and your access to the guess function, while the output is the required index or -1 if no majority exists. The output for this problem is an integer representing the index of the majority element, or -1 if no majority element is found. Let's explore some examples to understand this better. In the first example, the hidden array is 1, 0, 1, 1, 0. The majority value here is 1, as it appears 3 times out of 5, which is more than n/2, or 2.5. Valid outputs for this example are any indices of 1, such as 0, 2, or 3. In the second example, the hidden array is 0, 0, 1, 1, 0. Here, there is no majority element because neither 0 nor 1 appears more than n/2, or 2.5 times. As a result, the output is -1. These examples demonstrate how the function should behave depending on whether a majority element exists in the array. In the third example, the hidden array is 1, 1, 1, 1, 0, 0, 0, 1. The majority value in this case is 1, as it appears 5 times out of 8, which is more than n/2, or 4. Any index of 1, such as 0, 1, 2, or 3, would be a valid output. Let's also consider the constraints of the problem. The size of the array, n, is between 3 and 10,000, and the array contains only 0s and 1s. You are allowed to call the guess function at most 100*n times, so your implementation must be efficient and stay within this limit. Finally, remember that the majority element is defined as a value that appears more than n/2 times, and if no such value exists, your function should correctly return -1. Let's start by considering the brute force approach. The intuition here is straightforward: query every combination of indices to reconstruct the hidden array. For each index, we compare it with all other indices to determine the relative frequency of 0s and 1s. Once the entire array is reconstructed, we can identify the majority element and return it as the result. However, there are some key observations to keep in mind. Each query provides valuable information about how one index relates to others, but this method becomes highly inefficient because it requires querying every possible pair. When analyzing the complexity, we see that the time complexity is O(n) squared due to the pairwise comparisons, and the space complexity is O(n) to store the reconstructed array. This approach has significant drawbacks. It's impractical for larger arrays due to its inefficiency and involves unnecessary, redundant comparisons. To address these issues, we need a more optimized method, which brings us to the idea of using a divide-and-conquer strategy. By grouping queries and reducing redundant calculations, we can make the process more efficient while still identifying the majority element. Now, focusing on the divide-and-conquer strategy, there are important observations we can leverage. A majority element will dominate in any sufficiently large subset of the array. This means that instead of querying every pair of indices, we can reduce our workload by querying groups of 3 indices at a time. By doing so, we can deduce relationships between elements and track the frequency of 0s and 1s incrementally. Here's the step-by-step breakdown. First, we query groups of 3 indices, such as I plus 1, I plus 2. These comparisons help us identify consistent patterns, like which values appear more frequently. From there, we build the frequency count of 0s and 1s incrementally, without needing to reconstruct the entire array. Once all queries are complete, we can determine the majority element based on these counts. This method is much more efficient, as the time complexity is reduced to O(n). We only query a constant number of indices per step, and the space complexity is just O(1), since we only need to track counts. This approach eliminates redundancy and is well suited for larger arrays, making it both practical and efficient. Finally, let's discuss why the optimized approach is the preferred strategy. It strikes the right balance between efficiency and simplicity. By querying in groups of 3 and applying majority voting principles, we avoid the inefficiencies of brute force while maintaining accuracy in determining the majority element. The key insight here is recognizing that querying groups of 3 provides enough information to track the majority without needing to reconstruct the entire array. Another important realization is that majority elements dominate not just in the full array, but also in sufficiently large subsets. Of course, this approach involves some trade-offs. While it's significantly faster than brute force, it requires careful bookkeeping to track counts accurately. Additionally, edge cases, such as arrays with an even split of 0s and 1s, demand extra checks to ensure correctness. Overall, the optimized approach is ideal for this problem due to its linear time complexity, minimal space usage, and logical simplicity. While brute force might be easier to implement, its inefficiency makes it unsuitable for larger input sizes. By focusing on grouped queries and leveraging majority rules, we achieve an effective solution that balances performance and precision. To solve this problem, the first step is to clearly define what we are trying to achieve. The goal is to reconstruct a hidden binary array ARR of size n. We can't see the array directly, but we can use a query function, query I(j), which tells us whether two elements, ARR I and ARR j, are the same. Specifically, the function returns 1 if they match, and 0 if they differ. Using this tool, we need to determine two things: the reconstructed binary array and the majority element, the value, either 0 or 1, that appears most frequently in the array. The brute force approach to reconstruct the array starts by initializing an empty array of size n. Then, for each index I, we compare RR I with every other index j in the array. While iterating through these pairs, we maintain two counters, count_0 to track mismatches and count_1 to track matches. These counts give us insight into whether ARR I is more likely to be 0 or 1. After processing all indices, if count_1 for a given index exceeds count_0, we assign the value 1 to ARR I. Otherwise, we assign 0. This systematic comparison allows us to reconstruct the array step by step. Once the binary array is reconstructed, the next task is to identify the majority element. To do this, we simply count the occurrences of 0s and 1s in the reconstructed array. If there are more 1s than 0s, the majority element is 1. Otherwise, it is 0. Finally, we return both the reconstructed binary array and the majority element as the output. The querying mechanism plays a central role in this process, as it provides the information needed to determine how each index relates to others. By aggregating the results of these queries, we can infer the value at each position in the array. However, the brute force approach has a significant computational cost. Since we compare every element with every other element, the time complexity is O(n squared). This makes the algorithm simple to implement but inefficient for large arrays. Optimization opportunities include reducing redundant queries or applying statistical techniques to make smarter guesses about the array's structure. Edge cases, such as arrays of size 1 or arrays evenly split between 0s and 1s, should also be handled carefully. For instance, when n equals 1, the single element is trivially the majority, and when the counts of 0s and 1s are equal, either value can be validly returned as the majority. The algorithm relies on a few key data structures and operations to achieve its goals. The most important data structure is the array ARR, which holds the reconstructed binary values. Arrays are a natural choice here because they allow efficient indexing and updating. During the reconstruction process, we also use two counters, count_0 and count_1, to keep track of the frequency of matches and mismatches for each index. These counters are simple integer variables, but they are crucial for making decisions about the values in ARR. The main operations executed by the algorithm include the query function, frequency counting, and the majority check. The query function is the core operation, performed n squared times in the brute force approach. Each query provides binary feedback on whether two indices are similar, and this information is used to make inferences about the array's structure. Frequency counting is another key operation, as it allows us to aggregate the results of the queries and determine the value at each index. Finally, the majority check is a straightforward linear scan of the reconstructed array to determine the most frequent value, completing the process. Together, these data structures and operations enable the algorithm to systematically reconstruct the hidden array and identify its majority element. Analyzing the algorithm's complexity, the time complexity is n squared, due to the nested loop structure, where every index is compared with every other index. This quadratic growth makes the approach feasible for small to moderate values of n, but it becomes computationally expensive for large arrays. On the other hand, the space complexity is n, as we only need the reconstructed array and a few counters to keep track of frequencies. This ensures that the algorithm's memory usage remains manageable even as n increases. To improve efficiency, several optimizations can be considered. One way to reduce redundant queries is by leveraging symmetry. If query j has already been computed, there is no need to compute query j again. This can effectively halve the number of queries. Another potential optimization is to use statistical inference. For example, if we detect a strong trend in the majority values early on, we might reduce the number of queries for certain indices based on probabilistic reasoning. These improvements can significantly reduce the algorithm's runtime while still maintaining accuracy, making it more practical for larger input sizes. Here, we begin implementing the solution by defining the guess majority method inside the solution class. The first step is to determine the length of the hidden array using reader.length. We then initialize several variables, count_0 and count_1 to track the occurrences of zeros and ones respectively, and idx_0 and idx_1 to store the indices of one occurrence of each value. These will help us identify and differentiate between the two groups in the array. Next, we compare the first four elements of the hidden array against the first element, using the reader.query function. If the query returns 1, it means the element matches the group of the first element, so we increment count_1 and update idx_1. Otherwise, we increment count_0 and update idx_0. This process enables us to establish an initial understanding of the majority group among these four elements. We then use the counts to decide which group is the majority by comparing count_1 and count_0. The variable reference_idx is set to the index of a representative from the majority group, and the Boolean majority underscore is _1 tracks whether the majority group corresponds to the value 1. With this setup, we can now process the rest of the array efficiently. Now, we iterate through the remaining elements of the array, starting from index 4. For each element, we use reader.query to compare it with the representative of the majority group, identified by the earlier comparisons. If the result of the query matches the expected value for the majority group, we increment the corresponding count_1 for the group of ones or count_0 for the group of zeros. If the query result does not match, it implies that the element belongs to the minority group, so we adjust the counts accordingly. Once all elements have been processed, we determine the overall majority by comparing count_1 and count_0. If count_1 is greater, we return the index of a representative 1, idx_1, along with the count of ones. If count_0 is greater, we return idx_0 and the count of zeros. In the rare case where the counts are equal, we return -1 to indicate that no majority exists, along with the count of one of the groups. This completes our implementation of the guess majority function. Here, we begin by defining the Java implementation for the problem. We start with an interface named ArrayReader, which provides two methods, query and length. The query method allows us to compare four indices in the hidden array, and length gives us the size of the array. Next, we define the solution class and implement the guess majority method. Inside this method, we first retrieve the length of the array using reader.length. Then, we initialize several variables to help track the counts and indices of the two possible groups, count 1 and count 0 to count the occurrences of 1s and 0s respectively, and index 1 and index 0 to store the index of at least one occurrence of each group. To establish the majority group, we compare the first 4 elements of the array using the query method. For each comparison, if the query result equals 1, it indicates that the new element belongs to the same group as the first 3 elements, so we increment count 1 and update index 1. Otherwise, we increment count 0 and update index 0. This initial comparison sets the foundation for identifying the majority group. After establishing the counts and indices for the first few elements, we determine which group is the majority. If count 1 is greater than count 0, we know the majority group consists of 1s and set majority as 1 to true, using index 1 as the reference. Otherwise, the majority group consists of 0s, and we use index 0 as the reference. Now, we process the rest of the array starting from the 5th element. For each element, we perform a query with the first 3 indices and the current index. If the result indicates that the current element belongs to the majority group, we increment the count for that group. Otherwise, we increment the count for the minority group. This step ensures that we continue tracking the counts of both groups while verifying the consistency of the majority group across the array. By the end of this loop, we have tallied all elements and their group memberships. Finally, we determine the result based on the counts of the 2 groups. If the count of 1s is greater than the count of 0s, we return index 1, which points to an element in the majority group of 1s. If the count of 0s is greater, we return index 0 instead, which represents an element in the majority group of 0s. In the case where both counts are equal, meaning there is no clear majority, we return -1 to indicate that no majority exists. This ensures the function adheres to the problem's requirement of identifying a majority element or signaling that none exists. In this example, we are given a hidden array 1, 1, 0, 1, 0, with a length of n equals 5. Our goal is to find the majority group in this array using the reader.query method. To start, we initialize some variables, count_0 and count_1 to keep track of the number of 0s and 1s encountered so far, and idx_0 and idx_1 to store the most recent indices where we found a 0 or a 1, respectively. Initially, both counts are 0, and both indices are set to -1. Next, we compare the first 4 elements of the array by iterating through indices 0 to 3. For index 0, we call reader.query 0, 0, and receive 1, meaning the element at index 0 belongs to the group 1. We update count_1 to 1 and set idx_1 to 0. For index 1, reader.query 0, 1 also returns 1, so we increment count_1 to 2 and update idx_1 to 1. At index 2, reader.query 0, 2 returns 0, indicating this element belongs to group 0. We increment count_0 to 1 and set idx_0 to 2. Finally, for index 3, reader.query 0, 3 returns 1, so we increase count_1 to 3 and update idx_1 to 3. At the end of this step, we have count_1 equals 3 and count_0 equals 1 with the majority group being 1 so far. With the counts from the first 4 elements, we now determine the majority group. In this case, count_1 equals 3 and count_0 equals 1, so the majority group is clearly 1. We set reference_idx to 3, which is the most recent index of the majority group, and we define majority_ as _1 is true. Next, we process the remaining elements of the array, starting at index 4. Here, we call reader.query 0, 4, which returns 0, indicating that the element at index 4 is not part of the majority group. As a result, we increment count_0 to 2 and update idx_0 to 4. At this point, we have processed all elements in the array. To determine the final output, we note that the majority group is still 1, with a count of 3, and the index of the majority group is 3. Therefore, the final result is 3, 3, indicating that the majority group is 1 and its representative index is 3. Now, let's consider a second example where the hidden array is 0, 0, 1, 0, 1. The length of the array is again n equals 5, and we begin by initializing the same variables. Count_0 and count_1 are set to 0 to track the counts of 0s and 1s, while idx_0 and idx_1 are initialized to -1 to store the most recent indices where we encounter 0s or 1s. Next, we compare the first 4 elements of the array by iterating through indices 0 to 3. At index 0, we call reader.query 0, 0, which returns 1, so we increment count underscore 1 to 1 and set idx underscore 1 to 0. For index 1, reader.query 0, 1 also returns 1, so we increase count underscore 1 to 2 and update idx underscore 1 to 1. As we proceed, we will continue analyzing the remaining elements in the array to determine the majority group and its representative index. To analyze the time complexity, we can break down the solution into 4 main steps. First, determining the length of the hidden array involves calling the reader.length function once, which operates in constant time, or O1. Next, we compare the first 4 elements by iterating through them in a loop. Since there are only 4 comparisons and each query operation takes O1, this step also runs in O1 time. After that, the solution processes the remaining elements of the array, starting from index 4 up to index n1. This requires iterating through n4 elements, with each query operation taking O1. Therefore, this step contributes O(n) to the overall time complexity. Finally, the result is returned after performing some simple comparisons and assignments, which takes O1 time. By combining these steps, we get a clear picture of how the time complexity is distributed across the solution. When we add up the time complexity of all the steps, we have O1 for determining the array length, O1 for the initial comparisons, O(n) for processing the remaining elements, and O1 for returning the result. This simplifies to an overall time complexity of O(n). For the space complexity, the solution uses only a constant number of variables, such as count underscore 0, count underscore 1, idx underscore 0, idx underscore 1, and others, which means the memory usage does not scale with the size of the input array. Additionally, no extra data structures like arrays or lists are used in the solution. Therefore, the space complexity is O1, as the memory usage remains constant regardless of the size of the input. To put the current solution into perspective, let's compare it with a brute force approach. In a naive implementation, we would query every possible pair, I, j, in the array to determine the majority element. This would result in n squared queries in the worst case for an array of size n, leading to a time complexity of n squared. However, the space complexity of the brute force method would still be O1, assuming no additional data structures are used. On the other hand, the optimized solution significantly reduces the number of query calls by adopting a majority tracking strategy. Instead of iterating over all pairs, it uses a fixed reference index and processes the array in a single linear pass. This reduces the time complexity to O(n), while maintaining a space complexity of O1, as no additional memory is required. Now let's consider the best, average, and worst case scenarios for the optimized solution. In the best case, the majority group is unambiguously identified within the first 4 elements. However, the solution still needs to process all n elements to ensure correctness, so the time complexity remains O(n). On average, the solution processes all elements, resulting in O(n) time complexity. Similarly, in the worst case, the majority group is only determined after examining all n elements, which again results in O(n) time complexity. The reasoning behind this big O analysis lies in the fact that each query operation is independent of the array size and takes constant time, O1. Since the solution performs a single traversal of the array after the first 4 elements, the total number of query calls is proportional to n. Additionally, as no extra memory is used beyond a fixed number of variables, the space complexity remains O1. One of the most common mistakes when solving problems like this is not considering edge cases. For instance, you might overlook scenarios where all the elements in the array are identical, or when the array contains just a single element. These edge cases are critical because they often expose boundary condition errors. If these are not handled properly, they can lead to runtime failures or incorrect results. Another frequent issue is inefficient querying. This happens when you repeatedly query the same pair of indices or fail to use memoization to store results. Such redundant computations not only waste valuable resources but can also lead to exceeding the query limits set by the problem. Overlooking problem constraints is another pitfall. For example, ignoring limitations on the number of queries, the size of the array, or the valid input ranges can lead to time limit exceeded errors or runtime crashes.
Lastly, a significant error is incorrectly interpreting query results.
Misunderstanding how the queried values relate to the hidden array can result in flawed deductions and invalid outcomes. These mistakes highlight the need for careful planning and rigorous testing to ensure the solution is robust and efficient. Naive brute force is another common mistake where you attempt to solve the problem without any optimizations, such as binary search or leveraging mathematical patterns. While brute force can sometimes work for small inputs, it doesn't scale well to larger sizes, leading to inefficiencies and failures. To address this, it's helpful to recognize patterns in query-based problems. Often, these problems involve uncovering mathematical relationships or leveraging properties like symmetry or frequency distributions. Being mindful of your query budget is also crucial. Many problems place strict limits on the number of queries you can use, so optimizing your strategy to stay within those constraints is key.
Divide and conquer is a strategy worth considering, especially in problems involving searching or sorting.
Breaking the problem into smaller subproblems and solving them individually can reduce time complexity significantly.
In interviews, it's important to articulate your thought process clearly.
For each query, explain why you're making it and how you expect it to help solve the problem. Finally, don't underestimate the power of small test cases. Testing your ideas on arrays of size 2 to 5 can quickly validate your understanding of the query behavior before you dive into full implementation. As you explore related problems, you'll notice that some, like LeetCode 153, which involves finding the minimum in a rotated sorted array, share similar approaches, such as binary search. Others, like LeetCode 1011 or 410, focus on dividing workloads, making them great practice for understanding how to split and optimize operations. For instance, LeetCode 1482 involves finding the minimum number of days to achieve a specific goal, which often requires a mix of binary search and careful analysis of constraints. When considering alternative approaches, binary search stands out as a powerful tool when the problem involves a monotonic relationship. This method can drastically reduce time complexity compared to brute force, but it requires a solid understanding of the underlying property to implement correctly. Greedy methods are another option, useful for problems where making a locally optimal choice at each step leads to a global solution. However, you must always verify that a greedy approach is valid for the given problem.
Dynamic programming is yet another useful technique, especially for problems featuring overlapping subproblems or an optimal substructure.
While it's powerful, it often comes with higher memory usage and increased complexity in formulation, so it's important to weigh the trade-offs carefully.
Divide and conquer can also be applied to queries themselves.
By splitting the queries into smaller, disjoint ranges and then merging the results, you can optimize performance significantly. This approach is especially effective when the problem allows you to isolate ranges without overlap. However, it's worth noting that while this method can improve efficiency, it may also increase implementation complexity. Designing the logic to handle smaller ranges and then combine their results correctly requires careful planning and debugging, but it's a valuable technique for tackling problems with tight constraints.
Great job making it to the end.
Today, we discussed problem number 1538, guess the majority in a hidden array. We reviewed the brute force solution and highlighted the importance of efficiency in query-based problems. Keep practicing, stay curious, and don't forget to subscribe for more problem-solving tips.
See you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!